We are delighted to have Ted from University of Vienna, who will talk about shifted symplectic structures.
All right. Okay. So just to start off, this is all joined with Ludmil, who's, I guess he's not here right now, and Pranab Pandit. Okay. So the basic outline of what I want to talk about shifted symplectic and Lagrangian structures and the projectors kind of like this. Okay. I'm going to talk about shifted symplectic and Lagrangian structures, which are sort of recently discovered, I guess, structures on stacks, derived stacks and spaces, and especially on moduli spaces. And then Calabi Yau and relative Calabi Yau structures are coming in.
Looks a little bit strange. So let me see. Oh. There you go.
Okay. And then Calabi Yau and relative Calabi Yau structures, which are on structures on categories, which are sort of. Oops. All right. Anyway, they're structured on categories and everything. Sort of, they're the categorical versions of fucking stuff. But I can't go backwards. Nope. This goes automatically, doesn't it? I can hit the button. I can just use it.
You can probably use
yeah, okay.
This button.
I'll just stand here. Okay, cool. Okay, so I mean, yeah, I don't know. Preliminaries, the general characteristic zero. Symplectic stuff has to be over complex numbers, et cetera, et cetera. Everything's derived geometry. Okay. So shifted symplectic structures were, I mean, a lot of this stuff is from this PTVV paper, Pantev, Cohen, Becky, and Associate. So this is on a derived stack. So an n-shifted P form is basically, it's a section of the Pth wedge power of the cotangent complex, and then it's a cochain complex, so then we're in the degree n stuff, I guess. And then a closed n-shifted P form is a section of this negative cyclic Durand complex. And sort of, rather than tell you exactly what it is, I'll just say that the data of a closed n-shifted P form is a n-shifted P form, and then there's some other stuff too, such that the Durand differential of one guy is equal to negative of the internal differential of the next guy. So then an n-shifted symplectic structure is going to be an n-shifted closed tube form, which defines a quasi-isomorphism from the tangent to the cotangent complexes. So sort of in the standard case, I mean, so in the non-derived case, you have a isomorphism from the tangent bundle to the cotangent bundle, and then this is just the derived version of that. So the relative version is a Lagrangian structure, which is homomorphism to somebody with a n-shifted symplectic structure. And it's a homotopy of the pullback. So it's a homotopy between the pullback and zero, and then given such a homotopy, there exists an induced map from the tangent to the relative cotangent bundle, and we require that to be a quasi-isomorphism. So the main, or I guess the most important example is that it's not a ridiculous definition. So on a regular smooth scheme that you all know and love, a symplectic structure in the regular sense and a zero-shifted symplectic structure are the same thing. And then a submanifold is Lagrangian, sort of regular Lagrangian, if and only if the inclusion morphism has a Lagrangian structure, which is automatically unique. And for a more new example, I guess, you start with a Calabi Yau variety, and you take the moduli space of perfect complexes on the variety, and that has a 2 minus d shifted symplectic structure. So the 2 is coming from the space of perfect complexes in general is 2 shifted, and then you subtract the 2. And then so this is due to clock. But if you have a d plus 1 dimensional Foto, and then you take the effective anti-canonical divisor, so then the x in this case has to be.
Sorry, I missed
Sure.
I missed something. Right, d dimensional when d is not 3. You mean? I missed that probably from before.
So d dimensional. So this guy.
Yeah.
All right,
But d is
so-
not equal to 3.
I think the main example is when you have a K3, right, and it's d equals 2, and then it's a zero-shifted symplectic structure on the thing. So if you take a stable locus of that,
So do you mean that in the categorical sense, in the d-dimensional Calabi Yau, or?
Calabi, no, this is not categorical yet. This is just Calabi Yau in the sense of the canonical.
Okay.
Yeah. But yeah, just to keep going on my tangential comments, if you have a K30 and you take a stable locus of the perfect complexes, then that's sort of the fairly well-known Mukai symplectic structure. And then, what was that with this? Right, so the inclusion of an anti-canonical into a Foto, and then the anti-canonical divisor is Calabi Yau by the adjunctive formula. So then we have this pullback map from perfect complexes on Y to perfect complexes on X, and that has a Lagrangian structure. And then maybe to go sort of the other way, we recently showed that if you have a smooth Calabi Yau and then a smooth divisor in it, then the push forward map from perfect complexes on the divisor to the Calabi Yau also has a Lagrangian structure. All right, so I'm gonna pivot suddenly, or not so suddenly, to Calabi Yau structures, and maybe as a motivation, let me say the previous 2 examples. They're maps of spaces, but they're sort of obviously come from functors or maps of categories or what have you. And I want to, in some situations, say, oh, if this category has some structure, then the moduli space has this structure, or if this functor has a structure, then the map of the moduli spaces has this Lagrangian structure. And so, I'm sort of skipping some things. So let's say C is a saturated category, and then there's a lot of nuance which I'm skipping by restricting to this case. But the following are all basically equivalent. So there are trace pairings sort of from in the situations you'd expect. So trace of F times G mapping to the ground field, and then there's some symmetries which I don't want to say. And this is all more or less equivalent to a map from the cyclic homology of the category to the ground fields, with satisfying some non-degeneracy. And then sort of dually, it's a map from the ground field to the negative cyclic homology of the category, which is non-degenerate. So maybe, all right, I don't really want to go back, but maybe remember back in page 2 where a symplectic form was some section of the negative cyclic chains, and it also was non-degenerate. So anyway, any of these are going to be a Calabi Yau structure of dimension D. Okay. So then, sort of secondly, if D has a Calabi Yau structure given by some map from the cyclic homology to the ground field, and we have a functor from C to D, then a relative Calabi Yau functor on that guy is going to be so homotopy from the pullback of this to 0. So I mean you have a composition from the cyclic homology of C to cyclic homology of D to K. And we want that to be 0, or homotopy to 0. And then we want there to be a sequence. So this sequence, so the first, for any ENF, or just functorially in ENF, we want Hom sets of C just going by A to the Homs of D, and then this duality is by the trace map. And there should be a minus D should be over there. But so we want this sequence to be a fiber sequence or an exact sequence or what have you. That's sort of the, it should be seen as being basically the same as the non-degeneracy for the coordinate structures. Tone and Zapier tell us there's a moduli of objects functor, which for a category gives you a stack parameterizing the objects of a category, because it's in the name. And then there's this result of Toby Dickerhoff and Chris Brown that says a d-dimensional Calabi Yau structure on the category gives you a 2 minus d shifted symplectic structure on the moduli of objects. So that, I mean, that's the categorical Calabi Yau. And then a relative Calabi Yau structure of the functors gives you a Lagrangian structure downstairs in the moduli of objects. Okay, so I mean, we sort of expect that the Lagrangian structures for the, the I pull back and the J push forward on the M perfs and the moduli of perfect complexes on the spaces should come from the relative Calabi Yau structures on the categories. But I'm going to talk about not these. I'm going to talk about so these are sort of B model functors, and then we have for the I pullback for the case of the anti-canonical going into the final variety. We have a mirror, which is for a Landau-Ginzburg model. You take the Fukaya-Seidel category of that, and the Fukaya category of a smooth fiber, and then there's this cat map going from the Fukaya-Seidel to the Fukaya, which is mirror to that. So Shil Ganatra showed in his thesis that the Fukaya category has a Calabi Yau structure, and it's sort of modulo some conjectures. It's a Calabi Yau structure. I mean, I don't want to actually explain this, but sort of he showed it on the level of Hochschild homology, and then there's an S1 action on the Hochschild homology, and then there's an S1 action on the symplectic homology, which is sort of well known. And if those are the same, which I think everyone sort of expects that they are, then there's an obvious Calabi Yau. So we have a theorem that says that this cat map from the Fukaya-Seidel to the Fukaya category has a relative Calabi Yau structure. Maybe I shouldn't call this a theorem when it's among other things. It's based on this conjecture that I just said, and also probably on some unpublished stuff. But sort of given that, it's a theorem. And the basic idea is that the Hochschild homology of the Fukaya category is the symplectic homology of the fiber, and the Hochschild homology of the Fukaya-Seidel is the vanishing cycles. And the weak Calabi Yau structure is given by the map. So you take the symplectic homology and you project onto just the regular homology, just projection onto the constants loops. And then of those, you just look at the zeroth homologies, just like the points. And then you take this, I call it the dream map, where it's just you take the points and you count them all up. So that's the weak Calabi Yau structure. Going on. So if you have a vanishing cycle that, if you have a vanishing cycle that maps to the zeroth homology, so in general it hits somewhere in this symplectic homology. But if it hits specifically the zeroth homology, then alpha is a path, or a one chain, or it's a sum of things, among them one changes. And so if you have a path, then the boundary is it's a plus point and a minus point. So then when you end up taking the degree of that, you get a plus thing and a minus thing. You sum them up and you get 0. And so another way of saying that is that the pullback of this eta is literally equal to 0, and then sort of the homotopy to 0 is just the trivial homotopy. And then I sort of mentioned the S1 actions or the cyclic homology, but sort of all the important things here are trivially acted on by S1. So then you can go to the cyclic homology without any fuss. And then for the non-degeneracy, okay, maybe I'll get into this later, but we have an exact sequence on top. Okay, I'll probably go back to this later. But we have an exact sequence on top, just even ignoring the L1s for now, from L2 to this cup cap L2, where cup is the right adjoint of this cap functor, and then that goes to the Serre functor shifted by minus d, and then sort of this is isomorphic because it's an adjunction, and then this is isomorphic by what a Serre functor is, and then if you read this top row and the bottom two, that's exactly the type of sequence we want. So the three functors, which sort of before I go on any further, the point of this is that irrespective of any homological mirror symmetry being proved or not, sort of the cap functor and the I pullback functor have the same properties which you would expect them to have in homological mirror symmetry. But it's sort of going for a more broad, unifying perspective, I guess, is all these functors, the pullback and the push forward and the cap have Calabi Yau structures. And is there anything else in common? And judging by the top of the slide, yes, there is. So we'll say a functor is spherical if it has these left and right adjoints and the cones of the units and the co-units of the adjunctions are autoequivalences. And then there's additional property which if the torrent guy is Calabi Yau, then we say it's a special spherical functor if this particular cone is the Serre functor shifted by minus d. So I guess I should have done this before, but this is exactly the property that I used in this non-degeneracy proof. So L2 this is identity of whatever, and this is the F upper shriek, F push forward, and then this is the Serre functor. So that's exactly what I used. So the pullback and the push forward and the cat map are all special spherical functors.
Sorry.
Yeah.
So just a quick question.
Sure.
I just want to understand the generality. So at the moment I lower I upper star and G lower star are maps, so the functors from where to where?
So yeah, sorry. I mean it's not in. I mean it's really only in these two cases, or not of the M's, but of the regular perps here. These guys.
They're reduced for essentially the user future?
Yeah. And sort of in this particular case where X in either case is Calabi Yau.
So usually when there is a geometrical divisional illusion, then the usual push forward and pull back are spherical functors. So this is sort of categorical equivalent of that, right?
I mean, yeah, they're always spherical functors.
So here, usual divisor of T to the right X, the intersectional sequence, then that direct image and so pull back are spherical functors.
Yeah.
So this is a sort of this very general categorical. You're getting a categorical illusion.
we're sort of only interested in the case where the target is Calabi Yau anyway.
So I'm looking at my understand more start M per 1.
Yeah.
That's 1 per 1.
Sorry, we go for it.
So you see the circle functors.
Yeah,
There
sure.
are two different I upper stars. One is perf x to perf y, the other is m perf x to m perf y.
No, so sorry. This is it's. I mean, it's sort of a sloppy notation, but it's. I mean, what I mean is this is a functor from this category to that category, and this is the morphism from the moduli of objects in that category to the moduli of others in that category. I mean, I should have written m, so I started here.
So the statement is about M sub I or about
So
I?
the statement's about I.
It's about I, not M sub I.
Or I mean, we started about a statement with m sub I, and then we sort of lifted it to I. Or I don't know if lift is the right word here. Yeah. Anyway, so I guess what I want to say is if you have a spherical functor that happens to satisfy this additional thing, we're conjecturing that the functor has a natural relative Calabi Yau structure on it. Oh, I thought you were going to ask something. Okay. And that's, I think it's it. Oh yeah, so thank you all for listening. Are there any questions? Yeah.
So, Candid was in Miami last week, and I asked him the following question, but I also want to hear your answer. Is there any kind of a TQFT structure associated to these relative Calabi Yau?
Relative Calabi Yau.
Or do you expect?
I know I tried to do this at some point, but I didn't get anywhere.
Yeah, this is what Candid told me. Something like.
I mean, in the, I guess in the very broad sense that that you should get a TQFT for a Calabi Yau structure. I don't. Yeah. We tried to get a TQFT corresponding to relative Calabi Yaus, and we did it. And that's why this is only a conjecture at this point. I think if we manage to get a proper TQFT thing here, then I think we probably could. No, I guess it's not. As much as we want it to be, we can't do it.
But it might be that it's something not quite like a TQFT,
Yeah.
but close.
Right. Yeah. Yes. Okay.
What version of Spaide are you using this? I didn't quite understand.
Versions.
I mean, what is it? It's just some kind of.
That's a good question, because I heard it from Muhammad, and I don't really know a reference for it. Yeah, sorry, it's Seidels. Okay.
Okay.
Thanks.
It's not like construction.